motion along a straight line. See here the motion of the body is restricted into a straight line. So in order to represent the position of the body, we will have to choose an origin. Okay, and the line along which the body is moving can be chosen as the x-axis, or even you can choose that line as the y-axis or z-axis. But here the motion is restricted into a line, so let us choose that line itself as the x-axis. So then see, the position of the body on that straight line can be represented by its x coordinates. Suppose this is the origin, x equal to 0. So any point on the right side of this origin will be represented by a positive coordinates, and any point on the left side will be represented by a negative coordinates. As the motion is restricted to this line, only one coordinate, that is the x coordinates, will be necessary to represent the position of the particle. But when a body is moving in a plane or a surface, see, we will have to use two coordinates to represent the position of the particle. Suppose the two coordinates are x and y. Then the x and y axis must be intersecting at the origin, and any point on that plane can be represented by two coordinates, x and y coordinates. But when a body is moving in three-dimensional space, we will require three coordinates, say x coordinate, y coordinate, and z coordinates. When the motion is restricted to a line, that line itself can be chosen as the x-axis. But when the body is moving in a plane, you will have to choose two axes, and those two axes must be mutually perpendicular. When the body is moving in three-dimensional space, we will require three axes. All the three axes must be intersecting at the origin. Any line can be chosen as the x-axis or y-axis or z-axis. Only thing is that they must be mutually perpendicular and they must be in the counterclockwise order. Means, see, I have stretched my three fingers in three mutually perpendicular directions. See, if you choose this as the x-axis, then this will be y and this will be z. This also can be chosen as the x-axis. Then this will be y, this will be the z. Even this can be chosen as the x-axis. Then this will be y, this will be z. So the three axes must be mutually perpendicular and they must be in the counterclockwise order. Now let us come to the measurement of time. See, for the measurement of time, you have to choose an instant as the origin, means t equal to 0. Any earlier moment must be represented by a negative time, and any later moment will be represented by a positive time. So time can be negative. Any instant can be chosen as t equal to 0. So any earlier moment must be represented by a negative time only. So time can be negative, but time interval can never be negative. See, here I have taken see, three axes. I have taken this as the x-axis, then this must be y, this must be z. This is the positive direction of x-axis, so opposite will be negative. This is the positive direction of y-axis and this will be negative. Okay, and this is the positive direction of z-axis along the outward normal to the plane of the board. So along the inward normal, it will be the negative direction of z-axis. Okay. Now state of rest and state of motion. See, when can we say that a body is at rest? See, a body is said to be at rest if its position remains unchanged with respect to its surroundings in the course of time. When can we say that a body is in motion? When its position changes with respect to its surroundings as the time passes. But the state of rest and state of motion are relative terms. No body can be in absolute rest. No body can be in absolute motion also. See, consider a train, okay, started to move from a station. There are two passengers, say A and B sitting. This is A and B sitting inside the moving train. See, as seen by A, the passenger B is at rest. But for an observer outside the train, suppose this C is standing on the platform and the train is moving. So as seen by C, this passenger B is inside the train and the train is moving, passenger B is moving. So if we ask whether B is at rest or B is in motion, A will say B is at rest. C will say B is in motion. So the passenger B is at rest and at the same time B is in motion. With respect to A, B is at rest. With respect to C, B is in motion. So the state of rest and state of motion are relative terms. See myself now standing at rest. So with respect to these surroundings, myself at rest. But see, this building itself is on the surface of earth and the earth is revolving around the sun or rotating about its own axis. So all the objects on the surface of earth are in motion. But with respect to earth, see, this building is at rest, myself is at rest with respect to the surroundings. Okay. See, in general, in order to represent a point or the position of a particle in three-dimensional space, we will require three coordinates: x coordinates, y coordinates and z coordinates. Okay. Now see, suppose this is the x-axis. Okay. On the floor, okay, this line, x-axis. This is the y-axis and this is the z-axis. Okay. See, x-axis, y-axis and z-axis. Now consider a point. See, say 1, 2, 3. X coordinate is 1, y coordinate is 2 and z coordinate is 3. Okay. So from the origin, see, I have to move 1 unit along the positive direction of x-axis. So this is x-axis. Plane normal to x-axis will be yz plane. Okay. So this is x-axis. Here, this is x-axis. So a plane normal to x-axis will be yz plane or plane parallel to yz plane. Okay. So I have moved 1 unit along the x-axis. So on this side, x will be more than 1. On this side, x will be less than 1. So if I keep a plane, vertical plane like this, everywhere on that plane, x will be equal to 1 or x is fixed. So if a particle moves over this plane, its y and z coordinates will be varying with time. Okay, so its x coordinate is fixed, y and z will be varying, motion will take place in a plane. So any two of the coordinates are varying with the time, then the motion will take place in a plane and it is said to be two-dimensional. Okay, so I have moved 1 unit along the x-axis, then the position is on the floor. See, 1 unit towards the right of the origin. Now see, from the ground I have moved, see, 2 meter along the y direction. Okay, so if I draw a line like this on this plane, okay, to the right of this plane x is more than 1, to the left of this plane is x is less than 1, everywhere on this plane x equal to 1. I have drawn a line like this, everywhere on that line y equal to 2 and x equal to 1. So if x equal to 1, that is fixed, y equal to 2, that is also fixed, then the body can move only along this line. On that line, only the z coordinate will be varying. So if any two of the position coordinates are fixed and only one of the coordinates varying with the time, the motion will be along a straight line and it is called one-dimensional. Okay, so let me repeat, this is the origin. If I move 1 unit along the x-axis, I can keep a plane here parallel to the yz plane. Everywhere on that plane x equal to 1 only. Okay, on this side of that plane x is more than 1, on this side x is less than 1. Everywhere on that plane x is fixed, y and z will be varying. So when a body is moving over that plane, its two coordinates will be varying, motion will take place over a plane, it is two-dimensional. Okay, now we are going to fix one more coordinate, that is y equal to 2. So x equal to 1 means the motion is restricted into a plane. Now y equal to 2 means I will have to draw a line over this plane. Okay, on the right side of this x is more than 1, on the left side of this x is less than 1. On this line, see, above this line y is more than 2, below this line y is less than 2. So if x equal to 1 and y equal to 2, the body can move only over this line. Okay, so that is one dimensional. Suppose none of the coordinates are fixed, means x, y and z, all the three coordinates are varying with time. Okay, then the body can move in three-dimensional space and it is called three-dimensional motion. Okay, now see, this is a plane. See, this is the x-axis. Okay, and this shaded plane is normal to x-axis. Okay, suppose this, see this distance, okay, from the origin to this plane, that is equal to, say, x equal to 1. Then everywhere on this plane x is fixed. Only the y and z coordinates will be varying. Okay, and now see the second is y equal to 2. Y equal to 2 means, see, this is y equal to 2. Okay, so if we draw a line like this, see, line like this, everywhere on that line x equal to 1 and y equal to 2. Okay, two coordinates are fixed. Motion will take place along a line. Okay, now see, one-dimensional motion, only one of its position coordinates vary with time. Two coordinates will be fixed. Motion takes place in a straight line. Okay, and in two-dimensional motion, only two of its position coordinates vary with time. One coordinate will be fixed. Two vary with time means one is fixed. Okay, motion takes place in a plane. And in three-dimensional motion, all the three coordinates vary with time. Motion takes place in three-dimensional space. Okay. See now, distance and displacement. See, distance traveled by a body is the change in position along any direction. See, here we are not considering the direction, or direction of motion is not relevant. See, it is the length of the path followed by the body from the initial to the final position. Okay, so suppose a body starts from this position A and moves to the position B. Okay, so if the body follows a path, like this, then the displacement is the length of the path followed from A to B. Whereas the displacement is the shortest possible path. See, shortest possible path from A to B. Means it will be a straight line drawn from A to B. If the body follows this yellow path, okay, say when the body follows this first path, distance traveled is the length of the path and displacement is the length of the straight line AB. So in the first case, distance is more than the magnitude of displacement. Suppose the body moves from A to B along this straight line itself. Then the distance traveled is the length of the straight line. Displacement is also the length of the straight line. So in this second case, when the body follows this straight line path, the magnitude of the displacement and the distance covered are equal. So suppose the body follows like this from A to B. Okay, distance traveled will be the length of this path, but the displacement is again the length of the straight line AB. Means between two given positions, displacement is unique. Displacement has only one value. That is the shortest possible path from the initial to the final position. So change in position along any direction, that is the distance traveled. Okay, it is the length of the path followed by the particle from the initial to the final position. Okay, see, this distance is a scalar. It is measured in meter and must be having the dimensions of length. Then displacement, a change in position in a given direction or particular direction, that is displacement. Okay, and it is the shortest path from the initial to the final position. Okay, now see, distance is a scalar, displacement is a vector, so the displacement will be having both magnitude and direction. So while comparing displacement and distance, say displacements over distance. displacement over distance. See, when the body follows the first path, distance is more, displacement is less. When the body follows the second path, that is the straight line path from A to B, distance and displacement are equal in magnitude, or they are numerically equal. So we cannot say displacement and distance because these two are two different quantities. One of them is scalar and the other is vector. So we can take only the numerical ratio. This displacement, that is the quantity on the numerator, sometimes it may be equal and sometimes it may be less than the denominator. So this ratio will be always less than or equal to 1. That numerical ratio can be either less than or equal to 1, means it can never be greater than 1. Now see, consider the properties of distance travelled. See, distance travelled, it is also called the path length. Okay. See, it depends on the path followed. It depends not only on the initial and final position. It depends also on the path followed. Okay, then see, it's a scalar measured in meter and it has a dimension L. Okay, dimension of length. See, now the distance travelled or the path length can increase with time. It can remain constant with the time, but it can never decrease with the time. See, suppose a body has started from the position A. Okay, it has moved 5 meters towards right. Okay, then it remains there for some time. So the distance travelled will remain constant at 5. After that, when it comes back by 3 meters. Okay, so the distance travelled will be 5 in the forward direction plus 3 in the backward direction. Means distance travelled will become 8. Or the distance travelled can never decrease with time, and once the motion is started, distance travelled can never become 0. Okay, so can increase or can remain constant with the time, but cannot decrease with time. Okay, then may be greater than or equal to displacement, but can never be less than displacement. Now let's consider the properties of displacement. See, the first property is the definition itself. It is the shortest path length from the initial to the final position. See, suppose a body moves from the position A to the position B, following the first path, that is yellow path. Okay, so distance travelled is the length of this path, but the displacement is the length of the straight line, that is white line. Okay, see, if it follows any of these 3 paths from A to B, in all the cases, displacement is the length of the straight line AB. Okay, now it is a vector measured in meter and it has the dimensions of length. Then it can increase, it can decrease with time. Okay, unlike distance travelled. And it can remain constant with the time. Suppose body has started, say, from this position A, and it has moved towards right by 5 units and reaches B. Okay, as it moves like this, 1, 2, 3, like that, displacement increases with time. Okay, suppose it remains at rest at this position x equal to 5 for some time, then the displacement remains constant. But when it goes back, see, the displacement is shortest path from the initial to the final position. See, in displacement we will consider only from where the body has started its motion and ultimately where it has reached. So when it goes back from B, okay, displacement decreases. So first displacement is 5 units, then when it returns to 4, the displacement is only 4. Okay, when it reaches here, the displacement is only 3. Okay, and when it returns to the starting point, displacement becomes 0. So the displacement can increase with time, can remain constant with time, can decrease with time, and displacement of a body can become 0 when it returns to the starting points. So displacement, we should not consider the path followed. Okay, see, we have to consider only the shortest path from the initial to the final position, irrespective of the path followed. Okay, now see, can be positive or negative or 0. Okay, now suppose the body has started from B to A. Okay, initial position is represented by 5 and final position is represented by say 0. A is 0. Now displacement is the change in position. In physics, change we find always final value minus initial value. So if the body starts from x equal to 5 and moves to x equal to 0, then the displacement, change in position, means final position minus initial position. Final position here it is 0, initial position 5. So 0 minus 5 will be minus 5. So displacement can be positive, it can be negative, and it can be 0 also if it returns to the starting point after some time. Okay, then it is independent of the path followed. Okay, that we already discussed, and it is independent of the nature of motion. What does it mean, nature of motion? See, suppose the body moves from the position A to the position B with a constant velocity. Displacement is 5 units. Suppose it moves from A to B with increasing velocity. Displacement is still 5 units. And suppose it moves from A to B with a decreasing velocity. Then also displacement is 5 units. So displacement between two given positions is independent of the nature of motion, whether it is moving with a constant velocity or it is moving with a constant acceleration or variable acceleration or variable velocity. See, that nature of motion we should not consider. Okay. Now see, it is independent of most important point. It is independent of the choice of origin. See, suppose the body moves from this position, say here it is A, initial position, and this is B, final position. Okay, I have chosen this as the origin, x equal to 0. So the initial position is minus 4 and final position is plus 4. What is the displacement? Final minus initial. So 4 minus minus 4, that is 8 units. Okay, when I take this as x equal to 0. Suppose I have taken, see this fluorescent color, please see. This is x equal to 0. Then minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7 and minus 8. Okay, body has started from x equal to minus 8 and ultimately it has reached at x equal to 0. What is the change in position? It's always final minus initial. X equal to 0 minus x equal to minus 8. 0 minus minus 8 is 8 only. And suppose we have taken this as x equal to 0. See, this blue, x equal to 0. Okay, then the final position will be x equal to 8. Again, the displacement is the change in position and it is 8 minus 0, that is 8 units only. Okay, so independent of the path followed, it is independent of the nature of motion and it is also independent of the choice of origin. Okay, next, displacement between two given positions is unique. See, while finding the displacement, you have to consider only two things: from where the body has started its motion and ultimately where it has reached. You should not consider the nature of motion. You should not consider the path followed. You should not consider the choice of origin. Means between two given positions, displacement has only one value, or the displacement we can say it is unique. Okay, and finally it can be less than or equal to distance traveled, but can never be greater than the distance traveled. Okay, see, consider this situation, this one. Okay, if it follows the first path, yellow path, distance is more than displacement. When it takes the second path, distance is equal to the magnitude of displacement. When it follows this blue path, again the distance is more than the magnitude of displacement. Okay, see, the magnitude of displacement can be equal to or less than the distance traveled, but it can never be greater than the distance traveled. Now see, speed. See, the rate at which the body changes its position along any direction, that is the speed. Okay, or let us say the time rate of change of position of a body along any direction is the speed, or it is the distance traveled by the body in unit time. Okay, so if we take this SI systems of units, then see, unit time means it is 1 second. So the speed will be the distance traveled in 1 second. And if we take the unit of time as 1 hour, okay, then the speed will be distance traveled in 1 hour. Okay, so see the time rate of change of position along any direction means the speed is a scalar. Okay, we are not taking the direction here, or the distance covered in unit time. Okay, it is a scalar measured in meter second raised minus 1, or you can measure it in kilometer hour raised to minus 1. Okay, now see, let us convert 1 kilometer per hour into meter per second. Okay, see, the conversion is direct. It is straight. Okay, see, 1 kilometer per hour means it is 1 kilometer divided by 1 hour. Kilo stands for 1000. So 1 kilometer means 1000 meter. And in the denominator there is 1 hour. And each hour is equal to 60 minutes and each minute in turn equal to 60 seconds. Okay, so this is 1000 meter divided by 60 minutes and each minute equal to 60 seconds. So this will be 5 over 18 meter second raised minus 1. So 1 kilometer hour raised to minus 1 equal to 5 over 18 meter second raised minus 1, or see, 1 meter second raised minus 1 is 18 over 5 kilometer hour raised minus 1. Okay, now see, we have got this beautiful formula, speed equal to distance divided by time, but it is conditional. You can't use this formula everywhere and all the time. See, this is true only when the speed is constant. So speed equal to distance over time only when the speed is constant. Okay, now see, uniform speed. When can you say that a body is moving with a constant speed? See, body is said to be moving with a constant speed if it covers equal distances in equal intervals of time, however small these intervals may be. Okay, see, suppose we have started driving our car, say by 7 o'clock in the morning. Okay, after 1 hour, when we have checked the odometer at 8 o'clock, see, we have traveled 60 kilometers. Okay, when again we have checked after 1 more hour, say at 9 o'clock, again we have traveled 60 kilometers. And in every hour, see, the odometer is updated by 60 kilometers. Means in every hour, this car travels or covers 60 kilometers. Can we surely say that the car is running at constant speed? Say, see, we are checking the odometer after every 60 minutes. Okay, so, but it can be like this. See, during that 60-minute interval, suppose the body, see, after 60 minutes it has traveled 60 kilometer, but it can be like this. See, in the first half an hour, suppose the car has traveled 40 kilometer and the next half an hour it has traveled 20 kilometer. But after 1 hour, every in 60 minutes it covers 60 kilometer. See, but it can be like this. For the first half an hour it is at 40. And for the next half an hour it is at 20. So it is moving faster for the first 30 minutes and it is moving at half the speed for the next 30 minutes. If we have to say that it is moving at constant speed, see, this must be 30 kilometer in first 30 minutes and 30 kilometer in the next 30 minutes. Suppose every 30 minutes we have checked. In every 30 minutes it has covered 30 kilometer. Can we surely say that it is moving with a constant speed? Cannot. See, if we split that 30 minutes into, say, 10 minutes, 10 minutes and 10 minutes. After these 30 minutes, it has traveled 30 kilometers. But it can be like this. See, first 10 minutes it has traveled only 5 kilometers. Okay, next 10 minutes it has traveled 10 kilometers. And next 10 minutes it has traveled 15 kilometers. So it is not moving with a constant speed. Here it is very slow. Here it is moving with a moderate speed. And here it is slightly faster, let us say. If we have to say that it is moving at constant speed, see, in every equal intervals of time, it should cover equal distances, however small these intervals may be. Okay, so if we divide that time into 1 minute, 1 minute, 1 minute, in every 1 minute, it should travel the same distance. If we still divide that 1 minute into, say, 30 seconds, 30 seconds, 30 seconds, like that, in every 30 seconds, it should travel equal distances. Okay, So body is said to be moving with constant speed if it travels equal distances in equal intervals of time, however small these intervals may be. Okay, next see, we have to plot the graphs. See, for a body in uniform, body moving with uniform speeds. Okay, now see, let us plot the distance time graph. See, in mechanics, means see the branch of physics which deals with this motion, and see the motion with the motion of a body under the action of a force. See, the first quantity means in distance time graph, the first quantity will be plotted along the y-axis and second quantity along the x-axis. So distance time graph means distance along the y-axis and time along the x-axis. Velocity time graph means velocity along the y-axis and time along the x-axis. Okay, so from a graph, see, I tell you, we will have to find out two quantities. What is the physical quantity represented by the area under the graph? See, the physical quantity represented by the area under the graph, that is given by the quantity along the y-axis into quantity along the x-axis. Okay, and the next quantity we will have to find out from a graph is the physical quantity represented by the slope of the graph. Let me repeat, there are two quantities we will have to find out from a graph, only two quantities. What is the physical quantity represented by the area under the graph? What is the physical quantity represented by the slope of the graph? See, the physical quantity represented by the area will be yx, means the product of the quantity along the y-axis and the quantity along the x-axis. And the physical quantity represented by the slope of the graph will be delta y by delta x. See this small triangle, see, we have to read it as delta, and it is used to represent a small change. So this is a, see, the small change in the quantity along the y-axis over small change in the quantity along the x-axis. So here I have plotted distance time graph, means distance along the y-axis and time along the x-axis. So what would be the physical quantity represented by the slope? Okay, delta y means change in distance by change in time. It is nothing but speed. So slope of the distance time graph represents speeds. What would be the area? Area means a distance into time. That is not having any physical significance. We have not yet studied any quantity like that, distance into time. Okay, then here it is the speed time graph. Body is moving with a constant speed. Okay, speed remains constant. It is not increasing or not decreasing. Okay, it remains constant throughout the time. Okay, so see, the graph must be, if it goes up, speed is increasing with time. If it comes down, speed is decreasing with time. Here the speed is constant, so it must be a straight line parallel to the time axis. Okay, now see, what would be the area under the speed time graph? Okay, means the speed is plotted along the y-axis and time along the x-axis. So area will be quantity along the y-axis into quantity along the x-axis. Speed into time. It is nothing but the distance traveled. Okay. See, usually the bodies will be moving with variable speeds. See, while we drive a car, we cannot travel with constant speeds. Definitely we will be moving with variable speeds. So speed at different instance of time will be different, and the speed at a particular instance is called instantaneous speeds. In an automobile, see, the speedometer always shows the speed at that particular instance. Okay, now see, when a body moves with variable speeds, means if a body is moving with a constant speed, it travels equal distances in equal intervals of time. If a body covers unequal distances in equal intervals of time, or let us say if it needs unequal time to cover equal distances, then the body is said to be moving with a variable speed. In such cases, we express the speed in terms of average speed rather than see the instantaneous speeds. Okay, see, how do we find the average speed? It is the total distance over total time. Okay, see, there are two cases in finding the average speed. Suppose the total time of traveling is divided. That is the case 1, time is divided. Suppose the body moves with a constant speed v1 for a time t1. See, whatever equations we have studied for constant speed, that can be used from here to here because the speed is constant. For another interval of time, say t2, body moves with another constant speed v2. Okay, so see, all formula that is valid for constant speed can be applied from here to here, and it can be applied from here to here also, but constant speed formula cannot be applied throughout because speed changes from here. Okay, see, when the speed is constant, speed equal to distance over time. So distance will be the product of speed and time of traveling. Okay, so for the average speed, there is only one formula, that is total distance divided by total time, and it is unconditional. It is always true. Total distance divided by total time will give you the average speed. See, during the first interval of time t1, the distance traveled will be v1 t1. Okay, and during the next interval of time t2, see, this is the distance traveled during the first interval, and this is the distance traveled during the second interval, and the sum will give you the total distance traveled, okay, over total time t1 plus t2. That is the average speed. Okay, now suppose the total time of traveling is divided into two equal intervals, means t1 and t2 are equal, say each equal to t. So t1 equal to t2 equal to t. So here it will be v1t plus v2t over t plus t. So on the denominator it will be 2t, and on in the numerator we can take this t outside, and what comes inside the bracket, v1 plus v2. So we will get v average equal to v1 plus v2 divided by 2, and it is called the arithmetic mean. Okay, this AM, arithmetic mean of v1 and v2. Okay, now suppose the total time of traveling is divided into three equal intervals. Suppose the body travels for, say, 6 hours. Here it is divided into 3 hours, 3 hours. Okay, for the first 3 hours it travels with a speed v1, and for the next 3 hours it travels with another constant speed v2. So the average speed will be arithmetic mean v1 plus v2 over 2. Okay, now it is divided into 3 equal intervals, so that each interval equal to 2 hour, 2 hour, 2 hour, if the total time of traveling is 6 hours. For the first 1/3 of the time, it moves with a constant speed v1. For the next 1/3, it moves with another constant speed v2, and for the rest of the time, it moves with a constant speed v3. Okay, again, the average speed will be the arithmetic mean, that is v1 plus v2 plus v3 over 3. Now let us consider another case to find the average speed. See, here the total distance traveled is divided. Suppose a car travels a distance of 60 km. It is divided into two, distance is divided into two parts. Say, first 40 km is covered with a constant speed v1, and the remaining 20 km is covered with another constant speed v2. Okay, generally, see, distance s1 is covered with a speed v1, and s2 is covered with another constant speed v2. Okay, so the time required to travel distance s1 will be s1 over v1, and time required to travel s2 will be s2 over v2. Again, the average speed is always total distance over total time. Total distance will be s1 plus s2. Time for the first part of the distance, that is s1 by v1, and for time for the second part of the distance, that is s2 by v2. Okay, this is the average speed. Okay, average speed. This is average speed. It is unconditional. Okay, now suppose the total distance traveled, say in this case 60 km, it is divided into two equal parts. First 30 km at a constant speed v1, and the remaining 30 km at another constant speed v2. Okay, distance is divided into two equal parts, means s1 equal to s2 equal to, say, s. So s1 plus s2 will be 2s. Okay, here s by v1, s by v2. S is common factor that we can take outside. So what comes inside the bracket, it will be 1 by v1 plus 1 by v2. Okay, this s and s get cancelled. Okay, then V average equal to 2 divided by 1 by V1 plus 1 by V2. Now see what you have to do now. See, hold this one, hold this and take to the left. So on the left side there will be 1 by V1 plus 1 by V2 and take this V average to the right. It comes in the denominator. So it will be like this, 1 by V1 plus 1 by V2 equal to 2 over V average. See, holding this, it is shifted to the left and V average to the right, to the denominator. Okay, so 1 by V1 plus 1 by V2 equal to 2 by V average, and see, this is called harmonic mean. See, harmonic mean, okay, of V1 and V2. Now when we simplify this, see, we will get V average equal to 2 V1 V2 divided by V1 plus V2. Okay, now suppose the total distance travelled is divided into 3 equal parts. See, in the example that we have considered, the total distance is 60 km. It is divided into 3 equal parts, means each part will be 20 km. Okay, so first 20 km is covered with a speed V1, next 20 km at a speed V2, and the last 20 km at a speed V3. So the average speed, again it will be the harmonic mean, 3 over V average equal to 1 by V1 plus 1 by V2 plus 1 by V3. And when you simplify this, this will be the result. You might have a tendency to write V average, this is equal to C3 V1 V2 V3 by V1 plus V2 plus V3, like this. It will not be correct. See, all the formulae and all the equations must be dimensionally correct. See, in the denominator, this is speed into speed into speed, means dimensionally it is speed cube. On the left side, V average means it will be having the dimensions of speed. V average will be having the dimensions of speed. So on the right side also, the dimension must be that of speed. See, in the numerator here, this is speed into speed, means speed square. In the denominator, speed plus speed will be speed only. So speed square by speed will have the dimensions of speed. So it is dimensionally correct. Here, if you write this is speed into speed into speed, it will be speed cube on the numerator. Denominator, speed plus speed will be speed only. So speed cube by speed will be having the dimensions of speed square on the right side and speed on the left side. It won't be true. But in this case, on the numerator, speed into speed into speed, it will be speed cube. In the denominator, see, each term will be having the dimensions of speed square. Speed square plus speed square plus speed square. That will have the dimensions of speed square. So numerator speed cube, denominator speed square. So it will be speeds. Okay, on the right side and on the left side also speed. So that will be numerically correct and that will be dimensionally correct. And see, one more thing. See, when you take this combination V1, V2, V2, V3, see, it goes cyclically. See, you should say V1, V2, V2, V3, and do not say V1, V3. You should say V3, V1. When you say the sides of a triangle, it must be AB, BC, and CA rather than AC. Okay, so everything goes cyclically, rhythmically, systematically. So it will be 3 V1 V2 V3 over V1 V2 plus V2 V3 plus V3 V1 rather than V1 V3. Okay, now see velocity. See, it is the time rate of change of position along a particular direction. Means we have to consider the direction also. Okay, that is the velocity. Okay, it is a vector that is measured in meter second raised minus 1 or kilometer hour raised minus 1. Then see, velocity can also be considered as the displacement in unit time. Okay, and this velocity equal to displacement over time. See, this is true only when the velocity is constant. See, this is true only when the velocity is constant. Okay, and a body is said to be moving with constant velocity if it covers equal displacements in equal intervals of time, however small these intervals may be. Okay, whatever displacement is covered in the first interval, the same displacement it should cover in all the successive intervals of time. Okay, now see, if a body covers unequal displacements in equal intervals of time or equal displacements in unequal intervals of time, means in the first second say it covers a displacement 5 meter, in the next second it covers 3 meter, in the third second it covers 5 meter. Okay, like that, if it covers different displacements in equal intervals of time, it is moving with variable velocity. See, when a body is moving with variable velocity, we say instantaneous velocity or average velocity. Okay, what is instantaneous velocity? See, when body moves with variable velocity, it will have different velocities at different instants of time. So, velocity at a given instance is called instantaneous velocity. Okay, and average velocity, it is always total displacement over total time. And that formula, average velocity equal to total displacement over total time, that is unconditional. Okay, now see, instantaneous velocity, that is ds by dt. Okay, ds by dt, differential of displacement with respect to time, and average velocity equal to total displacement over time. This is unconditional. Okay, always true. Now see, when can we say that a body is in uniform motion? When the body moves with a constant velocity. When a body is moving with a constant speed, we cannot say that it is in uniform motion. Body is said to be in uniform motion only if it moves with a constant velocity. Okay. Now see, uniform motion means the velocity is constant. Okay, velocity constant means equal displacements in equal intervals of time, however small these intervals may be. Okay. Now see, when the velocity is constant or the body is in uniform motion, see, velocity equal to, we can write velocity, here we are considering uniform motion or motion with constant velocity. So this formula will be valid. Okay, velocity equal to displacement over time. Okay, displacement divided by time, because the body is moving with the constant velocity. Okay, now body moving with the constant velocity means it moves along a straight line because its direction is to be constant. So it must be moving along a line, straight line, and with a constant speed along the same direction. If it moves towards right, it must be towards right only, always with the same speed along a straight line. Okay, now suppose body moves along this line, and that line, let us consider it as the x-axis, then its position at any time can be represented by its x coordinates. Okay, and t equal to 0, that is the origin for the measurement of time, can be chosen. See, any instant can be chosen as the origin for the measurement of time. So suppose the body starts from x0, initial position coordinates, okay, when time equal to 0. And after some time, say time equal to t, its position coordinate is x of t. Displacement is the change in position. In physics, change means always final value minus initial value, as I have told you earlier. Okay, so the displacement here, displacement is represented by capital S, that is equal to final position x of t minus initial position x of 0. Okay, and time equal to, see here it is t, velocity equal to displacement over time. Here it is valid because the body is moving with a constant velocity. So xt minus x0, that is the displacement divided by time. Okay, so see, from here we can write s equal to vt. Okay, s equal to vt. And from here xt minus x0 equal to vt, right? xt minus x0 equal to vt, right? xt minus x0 equal to vt. Okay, and xt, take this minus x0 to the right, so it will become xt equal to x0 initial position plus velocity into time. See, this x of t is the position of the particle after a time t, and x of 0 is the position coordinate from where the body has started its motion. See, once the motion is started, its initial position cannot be changed. means this x with the suffix 0, the initial position coordinate, it is a constant. Here we are considering uniform motion, means the body moves with a constant velocity. So v is also constant, but the time is a variable. As t varies, its position x of t also varies. So x of t is a variable and it depends on the variable t. Now see, this x of t depends on the variable t. We have to plot the position time graph. Means position is to be plotted along the y-axis and time along the x-axis. What would be the shape of the graph that we are going to plot? See, in order to find the position or see the shape of the graph, you have to, see, we are going to plot this equation. You have to replace the quantity to be plotted along the y-axis with y and quantity to be plotted along the x-axis with x. See, this x of xt that we are going to plot along the y-axis. So it is replaced by y. This x0 is a constant. V is also a constant. T is the quantity to be plotted along the x-axis. Okay, so it is replaced by x. So we have got this one. This is of the form y equal to mx plus c. What stands for m here? It is v, velocity. See, this is the standard equation of a straight line. Okay, m is called the slope of the line and c is called y-intercept. C is called y-intercept. Y-intercept means it is the y coordinate of the point at which the straight line cuts the y-axis. See, here this is the straight line, it cuts the y-axis here and its y coordinates will be this much, this distance, that is equal to c and is called y-intercept. What is the slope? It is being represented by m and it is the tangent of the angle made by the straight line with the positive direction of x-axis. See, this is the positive direction of x-axis. This is the line and it makes, say, this much angle with the positive direction of x-axis. So slope is defined as tan theta. So see, m, that is the slope, equal to tan theta. So when you compare this with the standard straight line equation, what stands for m here? It is v. Means the slope of the position time graph represents velocity. How do you find the slope? It is tan theta. Okay, now let us plot the displacement time graph of a body in uniform motion. Means body moves with a constant velocity. So we have to get the equation for displacement of a body in uniform motion. So displacement of a body in uniform motion, that is SC equal to Vt. We are going to plot the displacement time graph. Means, as I have told you earlier, the first quantity, here it is the displacement, must be plotted along the y-axis. So in the equation, the quantity plotted along the y-axis, that is displacement, should be replaced by y. V being a constant, see, we should not change it, and t is the quantity plotted along the x-axis, so you have to replace this t by x. So we have got y equal to vx plus nothing, means plus 0. So again, this is of the form y equal to mx plus c. What stands for m here? It is velocity. So the slope of the displacement time graph also represents velocity. See, what stands for y-intercept here? It is 0. Means the y coordinate of the point at which the line cuts the y-axis is 0. Means, see, this distance is 0. Means the line should pass through the origin. Okay, this is theta, so the slope will be tan theta. See, the slope of the displacement time graph represents velocity. Slope of the position time graph represents velocity. Means both the position time graph and the displacement time graph must be of the same shape. Okay, so this is a straight line inclined to the time axis. This is also a straight line inclined to the time axis. They must be equally inclined to the time axis. The only difference is the y-intercept. See, in this case, this passes through the origin. In this case, it is having some non-zero y-intercept. And next, see, we have to plot the velocity time graph of a body in uniform motion. Uniform motion means velocity is constant. See, velocity is plotted along the y-axis and time along the x-axis. Velocity here remains constant in the course of time. See, as we move upwards, velocity will increase, okay, and it will decrease when we come down. But here the velocity is constant, so it must be a line parallel to the time axis. Okay, now see, velocity time graph of a body in uniform motion is a straight line parallel to the time axis. Let us find the area under the graph. See, for any area, there will be boundaries, or there must be boundaries. See, what are the four boundaries of area under the graph? See, one boundary is the graph itself. See, this is the y-axis, this is the x-axis, and this yellow line is the graph. So, one of the four boundaries is the graph itself, means this line. Two other boundaries are the two ordinates. Ordinates. Okay, suppose we want to find the area under the graph. So, from say T1 to T2. Okay, so this corresponds to time T1 and this corresponds to time T2. See, what do you mean by these ordinates? Ordinates are perpendiculars drawn to the x-axis from the endpoints of the graph. Here we have to find the area under the graph from T1 to T2. So, this is the point on the graph corresponding to T1. So, you have to drop a perpendicular from that point to the x-axis. Okay, so this is one of the ordinates. This is the second ordinate. Okay, this is the graph, and the fourth and last boundary is the x-axis. So, area under the graph means the area bounded by the graph, the ordinates and the x-axis. Okay, area bounded by the graph, the ordinates and the x-axis. Okay, now see, here it is a rectangle. Okay, and see, the height of the rectangle is equal to the velocity, and the breadth is T2 minus T1. Okay, so area will be velocity into T2 minus T1, or velocity into time interval, that is nothing but the displacement. So, area under the velocity time graph represents displacement. See, now the acceleration. The acceleration means the time rate of change of velocity, or let us say the change in velocity per unit time. Okay, in the SI system it will be the change in velocity per seconds. Okay, it is also a vector measured in meter second raised to minus 2. Meter second raised minus 2. Okay, if the acceleration is constant, then acceleration is equal to change in velocity divided by time. See, this is valid only when the acceleration is constant. When can we say the acceleration is constant? See, the rate of change of velocity is the acceleration. So, a body is said to be moving with the constant acceleration if its velocity changes equally in equal intervals of time, however small these intervals may be. Changes means if the velocity increases with time, then there is a change in velocity, body is accelerating. If the velocity decreases with time, then also there is a change in velocity, body is accelerating. If the velocity increases in the course of time, acceleration is called a positive acceleration. If the velocity decreases in the course of time, then the acceleration is negative. The negative acceleration is called deceleration or retardation. See, a body usually decelerates when it experiences a force opposite to the motion. Okay, so constant acceleration, okay, its velocity changes equally in equal intervals of time, however small these intervals may be, and the acceleration is a vector. It is measured in meter second raised minus 2. Now see, variable acceleration. See, if the velocity changes equally in equal intervals of time, then the acceleration is constant. If the velocity changes unequally in equal intervals of time, or if a body requires unequal intervals of time to change the velocity equally, then it experiences a non-uniform acceleration or variable acceleration. Okay, now see, when a body is moving with the variable acceleration, the acceleration will be different at different instants of time. So, acceleration at a particular instant is called instantaneous acceleration. And instantaneous acceleration is represented by dv by dt. dv by dt, differential of velocity with respect to time. Okay, so dv by dt, see I have written just like, see this is dv by dt, see this is dv, this is dt. Okay, see now I have added ds in the denominator. To cancel it, I will have to add ds in the numerator also. So this is nothing but dv by dt only. Now let me split it like this, ds by dt times dv by ds. S being the displacement, what is ds by dt? Rate of change of displacement with the time. Okay, so that is velocity. So velocity times dv by ds. That is another formula for acceleration. Okay, now when body moves with variable acceleration, it is interesting to find the average acceleration, and it is the change in velocity over time, and this formula is also unconditional. It is valid under any condition. Now see, let us discuss equations of motion. Means equations of motion for a body in uniformly accelerated motion. Here the body is moving in a straight line, and see, when time equal to 0, see, body's velocity is u and the position is x with the suffix 0. It is moving along this line with a constant acceleration, say a. After a time t, means when time equal to t, its velocity becomes v. Okay, and it reaches the position x with a suffix t. Okay, now what is displacement? By definition, it is the change in position. In physics, change is always final value minus initial value. So change in position means final position coordinate minus initial position coordinates. Okay, and acceleration, by definition, it is, here the acceleration is constant. So we can write acceleration equal to change in velocity by time only when the acceleration is constant. Here the acceleration is constant, so we can use that formula. See, change in velocity by time. Change in velocity, final velocity minus initial velocity, v minus u over t. Okay, now see this, take this t to the left, it becomes at equal to v minus u and v equal to u plus at. That is the first equation of motion. Okay, v is the final velocity or velocity of the body after a time t, u is the initial velocity, and a is the constant acceleration. Okay, now see, displacement s is equal to v average into time. See, I have told you average velocity equal to displacement by time is unconditional. Okay, from that formula we will get displacement equal to average velocity into time. That also will be unconditional. Means this is valid under any condition. Displacement is always the product of average velocity and time of traveling. Okay, now see, v average is the arithmetic mean of initial and final velocities. Yes, see, v average equal to u plus v divided by t. Even though this is a beautiful formula, this is valid only when the acceleration is constant. This is unconditional, but this is valid only when the, see this one, only when the acceleration is constant. Okay, now see, displacement equals u plus v divided by 2 into t, because here the acceleration is constant. Now this v, that v can be replaced by v equal to u plus at. See, s equal to u, I have written like this. Okay, now instead of v, v, I can write u plus at, right, whole divided by 2, that gives the average velocity, into t will give you the displacements. Okay, so s equal to, inside the bracket u plus u, that is 2u by 2 will be u only. Okay, here u, then at by 2, that is equal to half at, right, and outside the bracket there is t. When you multiply this, you will get ut plus half at square, s equal to ut plus half at square. See, when you put t equal to 2, you will get the displacement in first 2 seconds. When you put t equal to 5, you will get the displacement in first 5 seconds. Okay, S equal to ut plus half at square. Now S being the displacement, it is the change in position. In physics, change is always final minus initial. Final position coordinate. Here the body is moving along a straight line. That line itself can be chosen as the x-axis. So anytime the position of the body can be represented by its x coordinates. Okay, so the final x coordinate is x of t, and the initial x coordinate is with x with a suffix 0. So xt minus x0 is the displacement equal to ut plus half at square. From that we will get xt equal to x0 plus ut plus half at square. This x0 means the initial position coordinates. See, once the motion is started, the position from where it has started cannot be changed. Means x with the suffix 0 is a constant. Similarly, after starting the motion, the velocity with which it has started the motion cannot be changed. So u is also constant. Here the body is moving with constant acceleration, a is also constant. Okay, so the only variable on the right side of this equation is t. As t varies, this xt, position of the particle, varies accordingly. So we can say xt is a variable and this t is also a variable. If you want to find the position of the particle after say 5 seconds, simply you put t equal to 5, find the value of xt. Okay, so that is the equation for the instantaneous position. Okay, this gives the position of the particle at any time t after starting. Okay, now s equal to u plus v divided by 2 into t. This can be used because here the acceleration is constant. Okay, now average velocity is u plus v by 2. It is to be multiplied with the time to get the displacement. Okay, now see, what is the definition of acceleration? Acceleration equal to change in velocity over time. So a equal to v minus u by t. From here take this t to the left and a to the right. So we will get t equal to v minus u divided by a. See, put that value here, t equal to v minus u divided by a. So on the denominator, see, it is of the form v minus u times v plus u. So it is of the form a plus b into a minus b. It is nothing but a square minus b square. So v plus u into v minus u will be v square minus u square, and in the denominator it is 2 times a, 2a. Okay, so we got s equal to v square minus u square divided by 2a, or from that we can have 2as equal to v square minus u square, or v square equal to u square plus 2as. That is the third among the 3 equations of motion. Now see, we have got 3 equations. The first one is v equal to u plus at, and the second one is s equal to ut plus half at square, and finally v square equal to u square plus 2as. See, all these equations of motion can be applied only when the body moves with constant acceleration. Okay, so this s equal to ut plus half at square will give you the displacement in t seconds. Means when you put t equal to 3, you will get the displacement in first 3 seconds. When you put t equal to 5, you will get the displacement in first 5 seconds. Okay, now see, let us derive another equation. Suppose a body starts from the position O and moves with a constant acceleration. Okay, see, after 1 second it reaches at A. After 2 seconds it reaches at B. After 3 seconds at C. After 4 seconds at D. And after 5 seconds it reaches at the position E. So what is the displacement in first second? It is OA. What is the displacement in first 2 seconds? It is OB. Displacement in first 3 seconds, it is OC. So in S equal to ut plus half at square, when you put t equal to 3, you will get the displacement OC. When you put t equal to 4 in s equal to ut plus half at square, that is the only equation that we have right now, you will get the displacement in 4 seconds as OD. In s equal to ut plus half at square, if you put t equal to 5, you will get the displacement in first 5 seconds, that is OE. Okay, now what is the displacement in first 4 seconds? It is OD, that I have written here, displacement in 4 seconds equal to OD. What is the displacement in 5 seconds? That can be easily obtained by putting t equal to 5 in s equal to ut plus half a t square. That is, displacement in 5 seconds is OE. Okay, see, when the body reaches here, 4 seconds over, completed. Okay, 5th second, that interval starts from here, and at the end of the 5th second, body will be here. Okay, so the displacement in 5th second will be dE. Displacement in 5th second will be dE. Displacement in 4th second will be CD. Okay, so displacement in 5th second is dE. Okay, from this line, you can write dE equal to OE minus OD. Okay, what is OE? Displacement in 5 seconds. What is OD? Displacement in 4 seconds. So, displacement in 5th second equal to displacement in 5 seconds minus displacement in 4 seconds. Displacement in 10th second will be displacement in 10 seconds minus displacement in 9 seconds. Displacement in 6th second will be displacement in 6 seconds minus displacement in 5 seconds. Okay, so displacement, displacement in nth seconds will be displacement in n seconds. How do you get that? By simply putting t equal to n in s equal to ut plus half a t square. You can get displacement in first 10 seconds minus displacement in first n minus 1 seconds. How do you get that? You have to simply substitute t equal to n minus 1 in s equal to ut plus half a t square. Okay, so displacement in nth seconds equal to displacement in n seconds minus displacement in n minus 1 seconds. Here you have to open this bracket. So first will be u times n, un, then u times minus 1, it is minus u, then a by 2. See, what would be the expansion of n minus 1 whole square? You have to use the equation for a minus b whole square, a square minus 2ab plus b square. Okay, so this is first term inside the bracket will be n square. So a by 2 into n square will be a by 2 n square. Then second term will be minus 2n. So a by 2 into minus 2n. Okay, so minus a by 2 into 2n. And last term will be plus 1. So a by 2 into plus 1 will be a by 2 only. Okay, now we have to subtract these two. See, here there is un, no? Here there is un. See, there is un. Here also there is a un. When we subtract these two, they will get cancelled. Then one a by 2 n square. Here also there is a by 2 n square. Then minus of minus u. Okay, what is minus of minus u? Minus of minus u will be plus u, right? That I have written here plus u. Okay, then here it will be this 2 and this 2 can be cancelled. So it will be minus an. There is a negative sign outside the bracket. So it will be minus of minus an. So it will be an. Okay. Then finally we have a by 2. That is again there is a negative sign outside the bracket. So minus of a by 2 will be minus a by 2. Okay. Now see. Okay. Right. Now see, here we have u plus an minus a by 2. See, from these two terms, if you take a by 2 outside, what remains here? 2n. And what remains here? Minus 1. So u plus a by 2 into 2n minus 1. Okay. Now if you take a outside, then n minus half. U plus a into n minus half. Okay. So the Sn, displacement in nth seconds. Okay. U plus a by 2 into 2n minus 1 or u plus a times n minus half. Okay, and earlier we had an equation S equal to ut plus half a t square. Okay, this is the equation for the displacement in t seconds. Means here when you put t equal to 5, you will get the displacement in first 5 seconds. Here when you put n equal to 5, you will get the displacement in nth second or 5th seconds. Okay. Now we have got the equation for the displacement during the nth seconds. S with suffix n equal to u plus a by 2 into 2n minus 1, and it is for a body starts with an initial velocity u and moving with a constant acceleration a. Suppose the body starts from rest, means u equal to 0. see, when u equal to 0, displacement during the nth second will become a by 2 times 2n minus 1. Okay, so when you put n equal to 1, you will get the displacement in first second. When you put n equal to 2, you will get the displacement in second, and so on. So displacement in first seconds, let us say s with the suffix 1. See, a by 2 into 1, that is 2 minus 1 is 1. Displacement in the second, we have to put n equal to 2. 2 into 2, 4 minus 1, that is 3. Displacement during the third second, we have to put n equal to 3. 2 into 3, 6 minus 1, that is 5. So displacement in first second, second, third second, etc. will be in the ratio 1 is to 3 is to 5. If we cancel out the common factor a by 2, etc. up to 2n minus 1. 1 is to 3 is to 5 is to etc. up to 2n minus 1. So when a body starts from rest and moves with a constant acceleration, the ratio of displacements in first second, second, third second, etc. will be in the ratio 1 is to 3 is to 5. Okay, see, this is the ratio of displacements in first second, second, like that. 1 is to 3 is to 5 is to 7 is to. Okay, ratio of odd numbers beginning with the unity. See, what would be the displacement in first 2 seconds? First 2 seconds means displacement in first second plus displacement in second. Displacement in next 2 seconds will be displacement in third second plus displacement in fourth second. Like that, let us consider the ratio of displacements in first 2 seconds. See, first 2 seconds it will be 1 plus 3, 4. Okay, and next 2 seconds it will be 5 plus 7, that is 12. Next 2 seconds it will be 20. Okay, next 2 seconds it will be 28. Okay, next 2 seconds it will be, this is 36. Okay, and next 2 seconds it will be 44. Okay. So ratio of displacements in first 2 seconds, next 2 seconds, next 2 seconds, or successive equal intervals of 2 seconds each will be, see, what is the ratio? 4 is to 12 is to 20. This is nothing but, see, if we divide throughout by 4, it will be 1 is to 3 is to 5 is to 7 is to 9 is to 11. Right. Now let us consider the displacements in first 3 seconds, next 3 seconds, like that. Okay, see, in first 3 seconds it will be 9. Okay, if we add the displacement in first second, second, third second, next 3 seconds it will be 27. Okay, next 3 seconds it will be 45, and next 3 seconds it will be 63. Okay. Now ratio of displacements in first 3 seconds, next 3 seconds, next 3 seconds will be 9 is to 27 is to 45 is to 63. Divide throughout by 9. So it will be, see, 1 is to 3 is to 5 is to 7. See, it is true for 1 second, 1 second, 1 second. It is true for 2 second, 2 second, 2 second. It is true for 3 second, 3 second, 3 second. Means it must be true for any successive equal intervals of time. However, the duration of the interval may be. Now see, what do you understand by uniform acceleration? Means a body moves in such a way that its velocity changes equally in equal intervals of time. Okay, now consider a body starting from rest moving with constant acceleration. In first t seconds its velocity is increased by v, means it becomes v. After one more interval, after one more t seconds, its velocity again increased by v, becomes 2v. Okay, in next t seconds also it is increased by v, becomes 3v. Okay, so here the velocity of the body increases equally in equal intervals of time. When the body is moving with a constant acceleration, average velocity is the arithmetic mean of the initial and final velocities. And displacement is always average velocity into time. So here it will be, see, 0 plus v by 2. V by 2 is the average velocity and displacement will be vt by 2. Okay, in the next interval, 3v by 2 will be the average velocity. So displacement will be 3vt by 2. In the next interval, 2v plus 3v, 5v by 2 will be the average velocity into time. 5vt by 2 will be the displacement. See, here also vt by 2 is the common factor. Then the ratio of displacements will be again 1 is to 3 is to 5 is to 7, like that. See, this is valid when a body starts from rest and moves with a constant acceleration. Then the ratio of displacements in successive equal intervals of time will be 1 is to 3 is to 5 is to etc. up to 2n minus 1. Now see the beauty of this technique is that the same thing can be used in the reverse order also. Means when a body starts from rest and moves with constant acceleration, ratio of displacements in successive equal intervals of time will be 1 is to 3 is to 5 is to 7. In the reverse order, see, when a body comes to rest with uniform retardation, then the ratio of displacements in successive equal intervals of time will be, if there are 4 intervals, 7 is to 5 is to 3 is to 1. If there are only 2 intervals, then it will be in the ratio 3 is to 1. If there are say 5 intervals, then it will be 9 is to 7 is to 5 is to 3 is to 1. Okay, now see, here the velocity of the body is u. Okay, and see, during the first interval it loses half of its velocity. Then during the next interval its velocity will again decrease by half and become 0. Okay, so here to here the velocity changes by u by 2, again u by 2. Velocity changes equally in equal intervals of time if the acceleration is constant. So here the average velocity, here also it will be the arithmetic mean, because here also acceleration is constant, only thing is that it is negative. Even if the acceleration is negative, if it is constant, average velocity is the arithmetic mean of initial and final. Okay, so what would be the displacement? Initial plus final, that is 3u by 2. Half of it will be 3u by 4. That is the average velocity. Into time will give you the displacement. It is 3ut by 4. Okay, and here initially is u by 2, final 0. Average will be u by 4. Time traveling will be t, and displacement will be ut by 4. So if you divide throughout by the common factor ut by 4, ratio of displacement will be 3 is to 1, because there are only 2 intervals. Okay, see, here is another case. During the first interval, body loses 1/3 of its initial velocity. Next interval it again loses 1/3, and see, next interval it comes to rest. Okay, so it experiences uniform deceleration for 3 intervals. Ratio of displacements must be 5 is to 3 is to 1. Okay, here the velocity is u, initial velocity u, final velocity u, 2u by 3. Average velocity will be u plus 2u by 3 divided by 2. Okay, see, u plus 2u by 3 will be 5u by 3. Half of it will be 5u by 6. Okay, and displacement will be 5u by 6 into t. Okay, during the next interval, okay, this is 2u by 3 plus u by 3, that will be u, and average will be u by 2, and displacement will be u by 2 into t. Okay, means ut by 2. It is written as 3ut by 6, ut by 2. Okay, during the next interval, the average velocity will be u by 3 plus 0 by 2, that is u by 6, and displacement will be u by 6 times t. Okay, here also ut by 6 is the common factor. When you divide throughout by ut by 6, you will get the ratio as 5 is to 3 is to 1. Okay, now suppose body loses 25%, means 1/4 of its initial velocity after some time. Okay, say t. If it moves with uniform retardation, it loses the same amount of velocity during the next interval. Okay, so here it loses u 1/4 and it becomes 3u by 4. In the next interval t, it again loses 1/4 and becomes u by 2. In the next interval, it again loses 1/4 and becomes u by 4. And in the next interval, it comes to rest. Okay, so the velocity changes equally in equal intervals of time. Okay, body comes to rest with a uniform retardation in 4 intervals. So the ratio of displacement will be 7 is to 5 is to 3 is to 1, right? See, this is a wonderful question that appeared in the last question paper. Okay, see, there is a fixed wooden plank. A bullet is fired into the wooden plank and its velocity falls to 1/3 of its initial velocity after penetrating 24 centimeter. Okay, and it just comes to rest, okay, at the end of the block. It just comes to rest at the end of the block. Then what is the thickness of the block? Means it's given that here the velocity is u, and here the velocity is u by 3 after penetrating 24 centimeter, and suppose it has to penetrate an additional thickness, say x, where it comes to rest. So during this displacement, it loses 1/3 of its initial velocity. Okay, for that, suppose it takes a time t. Then how many such intervals must have elapsed, okay, before its velocity falls to u by 3? See, it is moving with a uniform deceleration, so its velocity must change equally in equal intervals of time. If it takes t seconds to lose the final u by 3, then it should have taken another t to lose the first u by 3 and another t to lose the second u by 3. Okay, so it must be like this. Here the velocity is 2u by 3. The time interval here is t and here is also t. So ratio of displacements will be 5:3:1. Ratio of displacements is 5:3:1. So this total is 5 plus 3, 8 parts. So see that 8 parts is equivalent to 24 centimeter. So that each part will be 3 centimeter. See, 5 plus 3, 8 parts of the total thickness will be of the total thickness is 24 centimeter. Then each part is 3 centimeter and the total will be 5 plus 3, 8 plus 1, 9. So the total thickness will be 9 into 3, 27 centimeter. Okay, you don't have to do any calculation. You can see by simply observing the question, you can answer it. Now see, let us consider some graphs. See, if we plot graphs, the shape of the graphs may be straight line, maybe parabola, maybe circle, ellipse, hyperbola, or it may be any arbitrary curve. See, one thing you have to understand is, if you plot an equation, see, in that equation you will have to replace the quantity plotted along the y-axis by y and quantity plotted along the x-axis by x. Okay, in that equation, if the maximum power of x and y both are 1, means there is no x square term, there is no y square term. See, for example, y equal to mx plus c. The maximum power of y is 1, no y square, y cube, etc. Maximum power of x is also 1, no x square, x cube, etc. Okay, or let us say ax plus by plus c. Such equations, this is equal to 0. Such equations are called linear equations. And when we plot this type of equations, the graph, the shape of the graph will be always a straight line. And only a straight line graph will have constant slope. Means the slope everywhere on that line will be the same. Okay, now see, consider, see, this is a straight line graph. It has a constant slope. Means everywhere on that line the slope is the same. Okay, everywhere on the line the slope is the same. See, slope at this point, slope at this point, slope at this point, slope at this point, everywhere on the line same slope. And one more thing, see, as we increase the quantity along the x-axis or as we move towards right, see, the graph goes up. Means as the quantity along the x-axis increases, the quantity along the y-axis also increases. Okay, the angle made by the straight line with the positive direction of x-axis is an acute angle less than 90 degree. The slope is positive. See here, the angle made by the straight line with the positive direction of x-axis, this is theta, this is greater than 90 degree. When the quantity along the x-axis increases, means as we move towards right, graph goes down. What does it mean? When the quantity along the x-axis increases, the quantity along the y-axis decreases. The graph is said to have negative slope. And in this case, see, as the quantity along the x-axis changes, there is no change in the quantity along the y-axis. Graph is again a straight line, so it must be having a constant slope. But the angle made by the straight line with the x-axis is 0, or it is parallel to the x-axis. then it is having a zero slope. Okay, so this is positive slope, this is negative slope, and this is zero slope. All the graphs are straight lines, and all of them are with constant slopes. Now let us plot the velocity time graph for a body in uniformly accelerated motion. I have told you earlier, in mechanics, the first quantity is to be plotted along the y-axis and second quantity to be plotted along the x-axis. So velocity time graph will be with the velocity along the y-axis and time along the x-axis. So we have to plot this equation, v equal to u plus at. V is the quantity to be plotted along the y-axis, so it is to be replaced by y. U is the initial velocity. Once the motion is started, it cannot be changed, means it is a constant, so I have written it as u itself. Then plus a, here the body moves with constant acceleration, so a is constant and t is the quantity plotted along the x-axis, so it is to be replaced by x. So we have got y equal to ax plus u. It is of the form y equal to mx plus c. Okay, what stands for m here? It is the acceleration, and m is nothing but the slope of the line. So the slope of the velocity time graph represents acceleration. Okay, and y-intercept is the initial velocity. So this is the graph in which the initial velocity u greater than 0 means it is positive, and acceleration a greater than 0 means acceleration is positive. Okay, and here initial velocity is again positive, u greater than 0, but the acceleration is negative. How do you represent it is negative? A less than 0. Okay, here see, body moves with a constant velocity, so the acceleration is 0. Now see the velocity time graph of a body starting with an initial velocity u and moving with a constant acceleration a means we are going to plot this equation, v equal to u plus at. Okay, so if we plot this equation, see, this will be the graph, right? See, there will be two quantities that we can find from a graph: the physical quantity represented by the slope of the graph, the physical quantity represented by the area under the graph. See, slope equal to delta y by delta x, and area equal to y into x, quantity along the y-axis into quantity along the x-axis. Here the graph is velocity time, means velocity along the y-axis, time along the x-axis. So the area represents velocity into time, means displacement. See, what are the four boundaries of the area under the graph? It is, see, one of the boundaries is the graph itself, then two ordinates. Ordinates means the perpendiculars drawn from the two endpoints of the graph to the x-axis. This is the graph itself, then this is one of the ordinates, and this is the second ordinate. Now we have got three boundaries. One more boundary is required, that is the x-axis itself, means this is the fourth boundary. Now that is the area bounded by the graph, and it represents displacement. And see, the shape of this area is that of a trapezium. How do you find the area of the trapezium? See, it is the average of the parallel sides. See, these two sides, this side and this side are parallel, and its average will be, see, OA plus DB by 2. Okay, see, average of the parallel sides multiplied by the separation between the parallel sides, or perpendicular distance between the parallel sides. See, perpendicular distance between the parallel sides is this one, or say this one. Okay, and it is along the x-axis time is plotted, so it will be from 0 to t, right? So that, or let us say this distance is OD. So area bounded by that trapezium will be OA plus DB by 2 into OD, and that area gives the displacement. See, what is OA? OA means this distance that represents the initial velocity u. Okay, and the next is DB. DB means this one, that is the final velocity v, or we can write it is u plus at, right? U plus at, final velocity u plus at. Okay, divided by 2 is the arithmetic mean or average velocity times t. Okay, that gives the displacement. So we will get S equal to ut plus half at square as the area under the velocity time graph, or it is the displacement of a body in uniformly accelerated motion. Now see, let us plot the displacement time graph of a body in uniformly accelerated motion. So this is the equation that we have to plot. S equal to ut plus half at square. S is the quantity to be plotted along the y-axis, so replace that S by y, and T is the quantity to be plotted along the x-axis, then replace T by x. So we will get y equal to u, initial velocity is a constant, a by 2 is also a constant, so we will get y equal to ux plus a by 2 x square. See, in an equation, if the maximum powers of both x and y are 1, equation is linear and the graph will be a straight line. See, if the maximum power of either x or y is 1 and the maximum power of the other is 2, means there will be, see, if there is y square, the maximum power of x will be only 1. If there is x square, then the maximum power of y will be 1. So if the maximum power of either x or y is 1 and the maximum power of the other variable is 2, then definitely the graph plotted will give you a parabola. Okay, so here see, the maximum power of y is only 1, the maximum power of x is 2, so if you plot this graph you will get a parabola. Okay, so this is the displacement time graph. See, the slope of the displacement time graph represents velocity. How do you find the slope? Slope is the tangent of the angle made by the graph with the x-axis. See, here the graph goes like this. The angle made by the graph with the x-axis, see, the angle made by the graph with the x-axis goes on increasing. So theta increases. As theta increases, tan theta will increase. Not only tan theta, see, when theta increases, sin theta will increase, tan theta will increase, secant theta will increase. Only the trigonometric function starting with a c will decrease. Means cos theta will decrease when theta increases. Cot theta will decrease. Cosecant theta will decrease. So all trigonometric functions starting with a c, cos, cosecant and cot, will decrease as theta increases in the first quadrant. That is why the derivative of see, all these functions, cos theta, cosecant theta, cot theta are negative. All other functions, means sin theta, secant theta and tan theta increases as theta increases. So anyway, here the angle made by the graph with the x-axis increases, then tan theta increases, means slope increases. The slope of the displacement time graph is velocity. So slope increases means velocity increases, means the body is accelerating. If the graph is a parabola, then its slope increases at a constant rate. Okay, and see, this is also a parabola. Here the slope decreases at a constant rate. Means here the angle made by the graph with the x-axis, see, angle made by the graph with the x-axis decreases. And finally it will become parallel to the x-axis, means the angle will become 0 finally, right? So here theta decreases, tan theta decreases, slope decreases, velocity decreases, means body is decelerating. So this will be the displacement time graph of a body which undergoes constant acceleration, and this will be the displacement time graph of a body which undergoes uniform deceleration. Now let us plot the position time graph. See, we have got S equal to ut plus half at square, and that S stands for the displacement, or it is the change in position. In physics, change means always final minus initial. So change in position will be final position minus initial position. So see, S equal to ut plus half a t square, and displacement is final position xt minus initial position x0. This is equal to ut plus half a t square. Okay, and take this minus x0 to the right, we will get x with the suffix t equal to x0 plus ut plus half a t square. Okay, now see, this x of xt, or the position after a time t, that is a variable to be plotted along the y-axis. So let us replace it by y. x0 is the position from where the body has started its motion. Once the motion is started, its initial position cannot be changed, so it is a constant. So x0 we will write it as x0 itself. Then u initial velocity also a constant. T is the quantity plotted along the x-axis. A by 2 is a constant. T again we have to replace by x. So finally we will get this, in which the maximum power of x is 2 and the maximum power of y is only 1. Definitely it will represent a parabola, means its a slope increases at a constant rate. In this case, slope increases at a constant rate means velocity increases at a constant rate, because the slope of the position time graph is velocity, means it is moving with a constant acceleration. Now see, this is a straight line with a constant slope. All straight lines are with a constant slope, and this is positive. Here the slope is negative, here the slope is 0. Okay, this is a parabola. Here the slope increases at a constant rate. Okay, this is also a parabola. Here the slope decreases at a constant rate. Okay, now see, we have to consider the motion under gravity. Okay, see, what is acceleration due to gravity? That is the uniform acceleration experienced by a freely falling body due to the attraction of the earth. Okay, and it is represented by small g equal to 9.8 meter second raised minus 2. It is equal to 980 centimeter second raised minus 2, or 32 foot second raised minus 2. Okay, see, in all our calculations we will take g as 10 meter second raised minus 2. See, what is this 10 meter second raised minus 2? When a body experiences an acceleration 10 meter second raised minus 2 means its velocity will change by 10 meter per second in each and every second. See, velocity changes means velocity can increase with time or velocity can decrease with time. When a body is projected vertically upwards, the body moves upwards and it is being pulled by the earth in the downward direction. Means the attraction of the earth opposes the motion, or earth's attraction discourages the body. So its velocity will decrease. In each and every second, its velocity will decrease by 10 meter per second. When it comes down, its velocity is directed vertically downwards and it is being pulled by the earth. So the attraction of the earth favors the motion, or the motion is being encouraged by the earth. So its velocity will increase. And the velocity increases by 10 meter per second in each and every second. Means, see, for example, I will show it here. Okay. Now suppose a body is projected with a velocity, say 30 meter second raised to minus 1, vertically upwards. After 1 second, its velocity will decrease by 10 and becomes 20 meter per second. After 1 more second, its velocity will again decrease by 10 and becomes 10 meter second raised minus 1. Okay, after 1 more second, its velocity will become 0. Means when body is projected vertically up with an initial velocity 30 meter per second, so 1 second, second second, third second, after 3 seconds its velocity becomes 0 and it reaches the maximum height. Even though its velocity is 0 at the highest point, it is still pulled by the earth towards its center. So it experiences an acceleration. It experiences a change in velocity. So it starts moving down. When it comes down, its velocity will be increased by 10 meter per second. Okay, so when it comes down, when it reaches here, its velocity will be again 10 meter second raised minus 1, but now it is directed downwards. After 1 more second, okay, it reaches here, its velocity will become 10 meter second raised minus 1, and after 1 more second, it reaches the point from where it has started its motion with the same speed, 30 meter per second. So when a body is moving under the effect of gravity alone, the speed with which it returns to the point of projection will be the same as the speed with which it has started its motion. Now see, consider this, a body is projected vertically up with an initial velocity u, and it is moving under the effect of gravity alone. See, at the highest point, capital H, its velocity falls to 0, okay, and see, it reaches a certain height small h, that can be any height in between, any height in between. So it reaches at height small h at time t after projection. Okay, so displacement is a vector from the initial to the final. So this is the initial position from where the body has started its motion, and this is the final position after a time small t. So let us apply the equation s equal to ut plus half a t square. Okay, yes, displacement is h. And what is the direction? From the initial to the final. This is the initial position and this is the final position. So it is directed vertically upwards, right? And initial velocity is also directed vertically upwards, u upwards. And what about the acceleration? See, acceleration due to gravity means it is the acceleration due to the attraction of the earth. No material body is repelled by the earth. All material bodies are attracted by the earth. So this attraction of earth or gravity always acts in the vertically downward direction, irrespective of the direction of motion of the body. When the body moves upwards, acceleration due to gravity is downwards. When the body moves downwards, then also acceleration due to gravity is downwards. Okay, so there are, see, displacement directed upwards, initial velocity upwards, and acceleration due to gravity directed downwards. There are, see, quantities directed upwards and also quantities directed downwards. So out of these two directions, upwards and downwards, you have to choose one direction positive. Any direction can be chosen as positive. Only thing is that opposite should be negative. So see, in this case, displacement s equal to h, that is directed upwards. I am going to apply this equation s equal to ut plus half a t square. Okay, then see, upward displacement h, I have written only h, means there is no minus or plus. What does it mean? It is that I have taken positive. Okay, if there is no sign, it means it is positive. So I have chosen upward displacement positive. So in this equation, that sign convention I have to follow. Means all the quantities directed upward should be positive. All the quantities directed downward should be negative. So initial velocity is also directed upward. That also I have to take positive. But the acceleration due to gravity is directed down. So I should take it negative. So h equal to ut minus g by 2 t square. I have taken this minus g by 2 t square to the left and ut to the left. So it will be g by 2 t square minus ut plus h equal to 0. Okay, see, this is of the form, this ax square plus bx plus c equal to 0, quadratic equation. This equation will satisfy for two values of x, and those two values of x are called the roots of this quadratic equation. Generally, in mathematics, we will take those roots as alpha and beta. And we know that the sum of roots alpha plus beta is minus b over a, and the product of roots alpha beta is c over a. Okay, now see, this is a similar equation. See, the only difference is that here the quadratic variable means instead of x, here it is t. So this equation will satisfy for two values of t. What does it mean? See, I have written this equation. See, when you look at this equation, what the feeling you should have? See, a body is projected vertically up with an initial velocity u. After a time t, if its displacement is h, then this equation is true. This equation becomes true for two values of t. Means the body will have the same displacement h at two instants of time, because t represents time. Let me repeat. See, if this equation satisfies for two values of t, means the body will have the same displacement at two instants of time. See, what is the physical significance? When the body is projected with an initial velocity u, after a time t, during the upward motion it reaches here and its displacement is h. Okay, displacement is h. When it comes down, see, it goes like this and after some time it comes down. During the downward motion, when it reaches the same position, its displacement is same. So the body has the same displacement h at two instants of time, one during upward motion and the other during downward motion. So what is this T1? T1 is from here to here. That is T1. What is T2? T2 again we have to start from the starting point. Again T2 will be from here to here, this total time. That is T2. Okay, so T1 and T2 are the roots of this quadratic equation. So T1 plus T2 will be minus B by A. What stands for B here? It is minus U. So minus B will be U only. By A, A means it is G by 2. Okay, so we have to divide with G by 2. G by 2. Okay, this 2 will come in the numerator. So T1 plus T2 equal to 2U over G, and the product of roots again C by A. What stands for C here? It is H. So H by G by 2, it becomes 2H by G. Okay. See, at the highest point displacement is capital H and it is directed from the initial to the final, means from here to here. Okay, so displacement S equal to H, it is direct upwards, final velocity V equal to 0. Okay, and let us apply this equation V square equal to U square plus 2AS, final velocity V equal to 0, U square, and see there is product AS, acceleration and displacement. See, acceleration is directed downwards and displacement is upwards. So one of these quantities will be positive and the other will be negative. So the product will be definitely negative. Okay, so 0 equal to U square minus 2GH. When you take this minus 2GH to the left, it becomes 2GH. That is equal to U square. So the maximum height when a body projected with an initial velocity U and moving under the effect of gravity alone, it is U square over 2G. Now this is the case 2 of motion under gravity. Here the body is projected vertically up with an initial velocity u. Here it is projected with a velocity u and it returns to the starting point after a time capital T. Okay, after a time capital T. We have to find the total time of traveling. Okay, see, S equal to ut plus half a t square. Suppose the total time of traveling is represented by capital T. See, when T equal to capital T, after a time capital T, what will be the displacement? It returns to the starting point, so the displacement is 0. So when T equal to capital T, displacement is 0. So you put S equal to 0 in S equal to ut plus half a t square and find the expression for the time. That will give you the total time of traveling. So S equal to 0. Initial velocity u is directed vertically upwards, that I have taken positive. Okay, ut, then half a. See, upward velocity I have taken positive. So the acceleration due to gravity that is directed downward should be taken as negative. Okay, see, there is a convention. When a body moves upwards, G is taken as negative. When body moves downwards, G is taken as positive. Nothing like that. See, if you take G negative during upward motion and positive during downward motion, how do you take when a body moves up and then comes down? 0. See, there is no convention like that. Irrespective of the direction of motion, acceleration due to gravity is directed always vertically down. Now you can take it positive or negative, that is only your choice. Only thing is that if you choose one direction positive, opposite should be negative. Okay, so here I have taken upward initial velocity positive, then I should take downward acceleration negative. So ut minus half g capital T square. When this minus g by 2 t square is taken to the left, it becomes g by 2 t square. This t and 1 t can be cancelled. Okay, then what do we get? 2u divided by g. This is the total time of traveling. Okay, and there is one more method. See, I will show you here. Suppose a body, okay, projected vertically up with an initial velocity u during the upward motion its velocity decreases, okay, reaches the maximum height with a velocity 0, and as it comes down its velocity increases at the same rate and reaches the starting point with the same speed with which it has started. Only thing is that initial velocity is directed upward, final velocity of same magnitude will be directed downwards. Okay, so initial velocity is u upwards, final velocity v. Okay, final velocity v, but that is numerically equal to u, it is directed down. Okay, acceleration throughout the motion, it is directed down. Okay, now let us apply this equation v equal to u plus at. Let us take upward direction positive, then we should take downward negative. Final velocity equal to u, but it is directed down, that I have taken negative, means it is minus u. Initial velocity directed up, so it is plus u. Acceleration due to gravity is downward, so it should be minus gt. When this minus gt is taken to the left, it becomes plus gt. When this minus u is taken to the right, it becomes u plus u, that is 2u, and t will be equal to 2u by g. Okay, that is the total time of traveling when a body is projected vertically up with an initial velocity u and it is moving under the effect of gravity alone. Means the effect of air resistance is neglected. Okay. Now this is case 3. A body is released from the top of a tower of height h. Okay, so the initial velocity u equal to 0, acceleration is g, it is directed downwards, and displacement when it reaches the foot of the tower will be h, that is equal to the height of the tower. Let us apply s equal to ut plus half at square, u equal to 0, so u 0, ut 0, and h equal to g by 2 capital T square, where capital T is the time after which it strikes the ground. Okay, so capital T equal to root of 2h by g. This is the time of free fall from a height h. Okay, so the body reaches the ground after this much time, and what is the speed with which it strikes the ground? Let us apply this equation v square equal to u square plus 2as. Initial velocity u equal to 0, and acceleration g, that is directed downwards, displacement h, that is also directed downwards, so we will get v square equal to 2gh, and the speed with which it strikes the ground is under root 2gh. Okay, this is another case. Body, see, instead of releasing, released means initial velocity 0, now it is thrown down. Okay, so it is having some non-zero initial velocity directed vertically down, so u is directed downwards, displacement h is from the initial to the final, means from the top to the foot of the tower. Okay, so displacement is directed downwards, acceleration due to gravity, it is always directed down. Let us again apply this s equal to ut plus half at square, so h equal to ut plus g by 2t square. Here u is directed down, h is directed down, g is also directed down, so all the quantities are directed down, so you need not take that downward direction as negative. You can, there is only one direction, that direction you can take positive. Okay, what comes next? Okay, this is the most beautiful case, case 4. Here, see, there is a tower of height h, and body is thrown vertically up with an initial velocity u from the top of a tower of height h. Okay, and see, it goes up until its velocity falls to 0 at the maximum height. After that it comes down. When it goes up, its velocity increases at a rate equal to g, means if g we take 10 meter per second square, during upward motion its velocity will decrease by 10 in each and every second, and as it comes down, velocity will increase at the same rate, means will increase by 10 meter per second in every second. Okay, now see, when it reaches the same level as the top of the tower, during downward motion its velocity will be u only but directed down. Okay, and when it reaches here, its velocity will be much more than that, u. And now let us apply this s equal to ut plus half at square. See, s equal to ut plus half at square we are going to apply for this body. Okay, s equal to ut plus half a t square. Here initial velocity, see, yes, displacement is directed down. That h I have taken downward, displacement I have taken positive. Downward direction positive. So initial velocity is directed upward, it should be negative, and acceleration g downward, so it should be positive. So we will get h equal to minus ut plus g by 2 t square. Okay, as an example, see this question you might have seen in the last question paper. That is, a body is projected vertically up with an initial velocity 4 meter per second from a bridge. Okay, it strikes water after 4 seconds. Body projected vertically up with an initial velocity 4 meter per second from a bridge, and it strikes water after 4 seconds. Now the question is, what is the height of the bridge? Okay, now see, it goes like this. It goes like this, and ultimately it reaches water. See, in s equal to ut plus half a t square, that s is not the distance travelled, it is the displacement. By definition, it is the shortest path from the initial to the final position. You should not consider the path followed. So the body has started from the bridge and ultimately it strikes the water. Okay, so the displacement will be this one. Okay, so displacement is directed vertically down. Okay, that is the height of the bridge h. This is downwards, that I have taken positive. So if there is any quantity directed upwards, it should be taken as negative. Okay, initial velocity 4 meter per second is directed upwards, so that must be minus 4, and time is 4 seconds. Okay, this is ut. Downward displacement I have taken positive, upward initial velocity I have taken negative. See, in this equation, same convention should be followed. Okay, ut I have written. Next term I have to write is half at square. Acceleration is that due to gravity, it is directed downwards and must be taken as positive. So this is plus half. Okay, then g is 10 and time will be 4 square. Okay, 4 square is 16 into 10 will be 160 by 2 will be 80, and this will be 4 into 4 16, 80 minus 16, it will be 64 meter. That is the height of the bridge. See, I will give you a beautiful idea. Means I am going to tell you a confidential matter that I have not yet told to anyone. That is, suppose a body is projected vertically up. Okay, projected vertically up with an initial velocity u equal to 10 meter second raised to minus 1. Okay, from the top of a tower of height 40 meter. Okay, after what time it reaches the foot of the tower, or it reaches the ground? After what time it reaches the ground? Let us see. Okay, see, the body will follow a path like this. Initial velocity u equal to 10 meter second raised to minus 1, and displacement is directed from the initial to the final irrespective of the path followed. So this is the initial position and final position is foot of the tower. So displacement is directed vertically down, this one. Initial velocity is directed vertically up, and throughout the motion acceleration is constant and it is due to gravity. So acceleration a equal to g, and let us take it 10 meter second raised to minus 1. Okay, this is directed downwards. So we have u, we have displacement s, we have displacement s, we have the acceleration also, and we want to find the time after which the body will be at the foot of the tower. Okay, means we have to find the time of traveling. Okay, so we have to take the equation connecting all these quantities. It is all of you know, s equal to ut plus half a t square, ut plus half a t square. Okay, downward displacement 40 meter, that I have taken positive. So initial velocity must be negative because it is directed upwards. So it is ut. plus g, acceleration due to gravity is 10, it is directed downwards. Downward displacement I have already taken positive, so this downward acceleration also must be positive. Okay, it is 10 by 2, it will be 5 t square. Okay, and throughout, see, this equation can be divided by 5 throughout. So what do you get? It will be, here it is 8, this is equal to minus 2t, and this is equal to t square, or let us say this will be t square minus 2t when comes to the left. Okay, minus 2t, t square minus 2t, and take this 8 to the right, so it will become minus 8, this is equal to 0. We can factorize this equation easily. Means the factors are there, sum must be minus 2 and products must be minus 8. See, the factors of 8 are 2 and 4. Okay, we should get minus 8, means one of these factors must be positive and the other should be negative. Then only we will get minus 8. So out of 4 and 2, one is positive and the other is negative. Their sum must be minus 2. Okay, so this larger number should be negative. So plus 2 and minus 4, plus 2 and minus 4. So the factors will be, okay, t plus 2 and t minus 4. This is equal to 0. T plus 2 into t minus 4, 0 means either t plus 2 equal to 0 or t minus 2 equal to 0, or both are zeros. Okay, if t plus 2 equal to 0, then t equal to minus 2. If t minus 2 equal to 0, then t equal to 4 seconds. Okay, now what is the answer? After what time the body will be at the foot of the tower? Okay, usually you do know what you do. This will be discarded because the time cannot be negative. I have, see, the beginning of the lecture I have told you time can be negative, but time interval cannot be negative. So you should not discard this value. This is having some physical significance. Of course, after projecting, after 4 seconds, the body will be at the foot of the tower. That is true. What is the significance of this negative sign? Suppose a body is projected. See, a body is projected with an initial velocity, say 30 meter second raised to minus 1, 30 meter second raised to minus 1. Okay, after 1 second, during upward motion, its velocity will decrease by 10 and becomes 20 meter second raised to minus 1. Okay, after 1 more second, its velocity will again decrease by 10 and becomes 10 meter second raised to minus 1. After 1 more second, its velocity will become 0. Okay, now see, during the upward motion, it moves with the constant acceleration. See, displacement is always the product of average velocity and time, but average velocity is the arithmetic mean of initial and final only when the acceleration is constant. Here the acceleration is constant during upward motion, even though it is negative. As the acceleration is constant, average velocity is the arithmetic mean. Here initial is 30, final is 20. Average will be 30 plus 20 over 2. That will be 50 by 2 means 25. And time taken by the body to move from this point to this point is only 1 second. So the displacement will be average velocity 25 into 1 second, it will be 25 meter. Okay, during this 1 second, initial 20, final 30, average is 15. 20 plus 30 by 2, 15. And time taken is 1 second, so this displacement is 15 meter. Okay, and see, this will be average is 10 plus 0 by 2, so this will be 5 meter. Okay, now when it comes down, okay, it travels 5 meter and acquires a speed 10 meter per second. Okay, after 1 more second, its speed becomes 20. After 1 more second, reaches the point of projection with the same speed with which it started its motion, that is 30 meter per second. Okay, now see, this motion, see, this is actually part of the motion that we have considered here. See, in that case we have considered only this much, and we have chosen this instant, see, this instant as t equal to 0 we have chosen. Okay. Okay, this instant we have chosen t equal to 0. See, any instant can be chosen as the origin for the measurement of time that I have told you in the beginning. Any earlier moment must be represented by a negative time, and any later moment must be represented by a positive time. So if you choose this moment as t equal to 0, then here it will be t equal to 1. Okay, here it will be t equal to 2, here it will be t equal to 3, here it will be t equal to 4. That is the time when it will be at the foot of the tower. Okay, and see, if you choose this as t equal to 0, this moment will be t equal to -1, and this moment will be t equal to -2. So when will the body be at the foot of the tower? There are two options. See, 2 seconds before it started its motion. See, actually this motion can be considered as one part of this motion. Okay, in that particular case, we have chosen this moment as the origin for the measurement of time. So the body will be at the foot of the tower at 2 instants of time, 2 seconds before and 4 seconds after. Okay, so hereafter you don't say that the time cannot be negative. Time can be negative. Time interval cannot be negative. Time interval means what is the time taken by the body to move from the top of the tower to the foot of the tower? It is 4 seconds. When will it be at the foot of the tower? Then we are asked for the time, not for the time interval. After what time will it be at the foot of the tower? Then we are asked for time interval, not for the time. Okay, so time can be negative, but time interval cannot be negative. Okay, now see, we have Galileo's law of odd numbers. This we have studied, already studied this s with the suffix n that gives the displacement of a body during the nth second if it starts with an initial velocity u and moves with a constant acceleration a. In case of a body falling freely under gravity, acceleration a equal to g, and if it is simply released, its initial velocity will be 0. So all the conditions for this particular equation will be satisfied in case of a freely falling body. So u equal to 0, a equal to g, displacement in the first second will be g by 2 times 1, displacement during the second will be g by 2 times 3, and displacement during the third second will be g by 2 times 5. So ratio of displacements during the first second, third second for a body falling from rest under the gravity alone will be 1:3:5 etc. So this must, as I have showed you earlier, this must be true for not only for 1 second, 1 second, 1 second, it must be true for any equal intervals of time. Only thing is that body should start from rest and should move with a constant acceleration. See that acceleration can be and the g also, okay, in this case, or any acceleration. The only thing is that it must be constant. Now see the distances traversed during equal intervals of time by a body falling from rest under gravity stand to one another in the same ratio as the odd numbers beginning with unity, and this statement is called the Galileo's law of odd numbers. Okay, this is another beautiful example for you. A body released from the top of a tower covers 7/16 of the total height during the last second of its fall. Now then, what is the height of the tower? That we have to find out, height of the tower. Okay, body released, okay, from the top of a tower of height h, suppose it reaches the ground after n seconds. Okay, now let us apply s equal to ut plus half a t square. It is released from the top where its velocity u equal to 0, displacement s equal to the height of the tower h, u0, ut0, and acceleration is g by 2, displacement h directed downward that I have taken positive, u0, ut0, okay, acceleration g, that is also directed downward. I should take it as positive, g by 2. Suppose it reaches the ground after n seconds, so g by 2 n square. Okay, see, if it takes 5 seconds, last second is 5th second. If it takes 4 seconds, last second will be 4th second. If it takes n seconds, last second will be nth second. Okay, so this much is 7h divided by 16. What does it mean? The total height is divided into 16 equal parts. Out of that, 7 parts are covered during the last 1 second. Okay, how many parts are remaining? 7 parts are this. So this remaining will be see, 16 minus 7 means this will be 9h divided by 16. See, total time of traveling is n seconds, out of which this much is travelled during the last 1 second. So this will be covered during the first n minus 1 seconds. Okay, so time taken by the body to move from here to here will be n minus 1. Initial velocity u equal to 0. So u0, ut0, displacement is 9h over 16. That is directed down, that I have taken positive. Initial velocity u0, ut0, acceleration due to gravity is directed down, g by 2 should take as positive. Okay, then the time is n minus 1 whole square, n minus 1 whole square. Now I have got two equations. Okay, see, this is equation 1 and this is equation 2. Okay, let me simply rewrite this second equation. See, 9 divided by 16. Okay, see, now I have to write this h. Instead of this h, let me replace h by g by 2 n square. So g by 2 n square. Okay, so I have written 9 by 16. Instead of h, I have written g by 2 n square. On the right side, see, there is g by 2 n minus 1 whole square. Okay, see, there is g by 2 on the left and g by 2 on the right. Now see what remains. 9 by 16 n square equal to n minus 1 whole square. When you see this, you must be very happy because on both sides there are perfect squares. So you can simply take the square root. See, it will be 3 over 4 n. This is equal to n minus 1. Okay, take this minus 1 to the left. So it will be plus 1. Okay, this is n minus 3 n divided by 4. This is equal to n over 4. So n equal to 4. Means the body will be at the foot of the tower after 4 seconds. Okay, now see, we have to get the height of the tower. N equal to 4. Put n equal to 4 here. N square is 16 into g is 10. 16 into 10 is 160 over 2, that is 80 meter. So the height of the tower is 80 meter. See, even without doing all these, you can easily find the answer. I will show you. See, a body falling freely under gravity covers 1 is to 3 is to 5 is to 7 is to 9, like that. Okay, it covers 7 by 16th. Okay, in that 7 by 16, that 7 is this 7 actually. Okay, see, in the 4th second it covers 7 parts of the displacement, and in 4 seconds means in 4 seconds means the displacement covered in first 4 seconds, that is 1 plus 3, 4 plus 5, 9 plus 7, 16. See, the sum of all these, this is 16. So 7 by 16th will be covered during the 4th second. Okay, see, for a freely falling body, if we take g equal to 10, first second is 5, then 15, then 25, then 35, then 45. Even before going to exam, you know all these things. G is 10. Okay, so first second 5, then 15, 25, 35, like that. Okay, and if the total time of traveling is n, here it is 4. So it will be g by 2, 5 times n square. Okay, so 5 times 4 square, 5 into 16, that is 80 meter. See, here we have another beautiful example. see, a wooden block is released from the top of a tower of height 100 meter. At the same time, a bullet is fired from the foot of the tower along the same vertical line with an initial velocity of 50 meter per second. Now the question is when and where the two will meet or strike, or bullet hits the block. Okay. And now see, suppose the bullet hits the block, say here. Okay. Then bullet from here, please listen, bullet from here and the block from here starts simultaneously. Okay, and both reach at this position at the same time. So the time taken by the bullet to move from here to here and the time taken by the wooden block to fall from the top to this position are same. Time of traveling of both the bodies are the same. Okay, now suppose the displacement of the bullet in the upward direction, okay, that is h1, and displacement of the wooden plank in the downward direction, that is h2. Okay, now what is h1? h1 displacement of the bullet that is directed from the initial to the final. From the initial to the final means h1 is directed upwards. I am going to apply sc equal to ut plus half at square. In that, yes, displacement is h1 that is directed upward, that I have taken positive, equal to initial velocity is directed upward, again I have to take positive, minus g by 2 t square downwards. Okay, and next body, that is a wooden block that is released and its displacement is from the initial to the final, means it is directed downwards. So displacement is h2. Okay, this is equal to it is released, means its initial velocity is 0. So for the block u0 ut 0 and it will be g by 2, time of traveling same, g by 2 t square. Okay, if you add this, means this h2 and this h1, when you add these you will get h1 plus h2 equal to the height of the tower, right? So h equal to h1 plus h2. See, what is h1 plus h2? ut minus g by 2 t square plus g by 2 t square. So h equal to ut. Okay, and the time after which the two will meet, it is h over u. This is 100 divided by 50. This is equal to 2 seconds. So the two will meet after 2 seconds. Okay, how long the block will fall in 2 seconds? I have told you, in the first second it will fall by 5 meter, next second 15, next 25, next 35, like that. But see, here it falls only for 2 seconds before they meet. So in the first 2 seconds, 5 plus 15 means they will meet 20 meter below the top of the tower, or let us say 80 meter above the foot of the tower. So the block and the bullet will meet each other, or let us say the bullet will strike the block at a height equal to 80 meter above the ground after 2 seconds. Now we have the wonderful concept of relative velocity. See, relative velocity of 1 with respect to 2 means velocity of 1 as seen by the second body, or velocity of the first body as observed by the second body. Okay, that need not be what we call the actual velocity of the first body. Okay, so v12, that is the relative velocity of first with respect to seconds, equal to velocity v1 minus velocity v2. Velocity being vectors, I have written all these as vectors. Means that there must be an arrow above it. Okay, so v12, that is the relative velocity of 1 with respect to 2, that is equal to v1 minus v2. Okay, here the motion is restricted into a line, so there will be only 2 directions possible. Okay, suppose body is moving along this line, so the velocity can be either towards left or towards right. There are only 2 possible directions. If the 2 bodies are moving along a straight line along the same direction, then the relative velocity is equal to their difference. Okay, if the 2 bodies are moving along the same line, see here we are considering motion only along a straight line. So when two bodies are moving in opposite directions, see, relative velocity will be v1 plus v2. Okay, that is the relative velocity. See, not only the relative velocity, relative acceleration, relative displacement, all the relative quantities we have to find. 1 with respect to 2 means the quantity of the first body minus the quantity of the second body, means displacement of 1 with respect to 2 means displacement of 1 minus displacement of 2. Acceleration of 1 with respect to 2 means acceleration of 1 minus acceleration of 2. See, the very important thing is that v equal to u plus at, s equal to ut plus half at square, and v square equal to u square plus 2as. All of you must be knowing to apply these equations when only one body is in motion. Means you can apply this v equal to u plus at or s equal to ut plus half at square or v square equal to u square plus 2as for the first body, and you can apply all these equations for the second body also. But see, all these equations, whatever equations you have studied so far in one-dimensional motion, can be applied for two bodies together if they are moving simultaneously. Only thing is that you will have to replace all the absolute quantities with the corresponding relative quantities. Okay, see, I will make it more clear. Means v equal to u plus at can be applied for the first body, or you can apply it for the second body. What I am telling you now, you can apply this equation for the two bodies together, only one equation for the two bodies, provided they are moving for the same time. Okay, then you have to replace all the quantities with the relative quantities. Means v12, final velocity of 1 with respect to 2. Then u12, initial velocity of 1 with respect to 2. a12, acceleration of 1 with respect to 2. See, here if the first quantity is 1 with respect to 2, all the quantities and in that equation must be in the same order. Means one quantity cannot be 2 with respect to 1. If one quantity is 1 with respect to 2, all the quantities in that particular equation must be 1 with respect to 2. Okay, means it need not be always 1 with respect to 2. You can take 2 with respect to 1 also, but you have to keep in mind that all the quantities must be relative and all the quantities must be in the same order. Okay, here displacement of 1 with respect to 2, initial velocity of 1 with respect to 2, acceleration of 1 with respect to 2. So all equations of motion can be applied for the two bodies together. Now see, we have an interesting example for the application of this relative motion. See, there is a bus which starts from rest and moves with a constant acceleration of 1 meter per second square. A man initially 48 meters behind the bus starts running at a constant speed of 10 meters per second to catch the bus. Okay, after what time will he be able to catch the bus? That is the question. Okay, now see, bus from here and man from here start simultaneously. Suppose after some time, bus and the man, okay, reaches the same position after say t seconds. Okay, so the displacement of the bus will be from here to here. Let it be x. Okay, bus from here and man from here start simultaneously. They must reach the same position at the same time. So if this is x, displacement of bus is x, displacement of man will be 48 plus x. What I have told you earlier. See, relative velocity of 1 with respect to 2 is v1 minus v2. Not only the velocity, displacement, acceleration, everything you have to find like that. Displacement of man with respect to bus means displacement of man minus displacement of bus. What is displacement of man here? It is 48 plus x. This is 48 plus x. And what is the displacement of bus? It is x. So relative displacement will be 48 plus x minus x. That is equal to 48. See, here I have taken man as the first body. Okay, so initial velocity of man is represented by u1. Acceleration of man is represented by a1. Here the man is running with a constant velocity, so his acceleration a1 equal to 0, initial velocity 10 meter per second. 10 meter per second, yeah. And bus starts from rest. So initial velocity u2 of bus equal to 0, and it moves with a constant acceleration. Bus we have taken as the second body, so its acceleration is represented by a2, and it is 1 meter second raised minus 2. Okay, what is the initial velocity of man with respect to bus? So it is u12, means u1 minus u2 by definition. So it is 10 minus 0 equal to 10 meter second raised minus 1. And acceleration of 1 with respect to 2, that is acceleration of 1 minus acceleration of 2. Acceleration of man is 0, acceleration of bus is 1. So acceleration of man with respect to bus will be 0 minus 1. It is minus 1 meter second raised minus 2. So all the quantities here are relative of man when the bus is taken as the reference. Now we are going to apply S equal to ut plus half at square for the man and bus together as a single equation. So all absolute quantities are to be simply replaced by the corresponding relative quantities. So relative displacement of man with respect to bus is 48. Relative initial velocity of man with respect to bus is 10. Relative acceleration of man with respect to bus is minus 1. So it will be minus half t square. Now you can multiply this equation throughout by 2. It will be 96 equal to 20t minus t square. Take that minus t square to the left and 20t to the left. So it becomes t square minus 20t plus 96 equal to 0. Okay. See, we can factorize this equation. There should be two factors. Their sum must be minus 20 and their product must be plus 96. So both the factors must be negative so as to get a negative sum and positive product. See, the factors of 96 are 8 and 12. So we can write t minus 8 into t minus 12 equal to 0. If the first factor is 0, t equal to 8. If the second factor is 0, t equal to 12. What does it mean? The bus and the man will come together after 8 seconds and again after 12 seconds. When they come together after 8 seconds, velocity of the man is 10 meter per second because he is running at a constant velocity of 10 meter per second throughout. But the bus starts from rest and moves with a constant acceleration, means its velocity increases by 1 meter per second in every second. So after 8 seconds when they come together, the velocity of the man will be 10 only, velocity of the bus will be 8 meter per second. So at that moment, man will overtake the bus. So for the next 4 more seconds, means from 8 seconds to 12 seconds, man will be ahead of the bus, running at a constant velocity of 10 meter per second. Bus will be accelerating. So after 4 more seconds, bus and man will again come together. At that moment, velocity of the bus will be 12 meter per second. The velocity of the man will be still 10 meter per second only. So after that, the man can never get into that bus. So there will be 2 chances for the man after 8 seconds and again after 12 seconds from the starting. Okay, and one thing you have to understand is that between 8 seconds and 12 seconds, man will be ahead of the bus. Okay. Okay, see, I will give you yet another wonderful example before I conclude. That is, see, a train of length 100 meter is running with a constant deceleration. It enters a bridge of length 1 kilometer with a speed of 63 km per hour, decelerates uniformly and leaves the bridge with a speed of 36 km per hour. What is the time taken by the train to cross the bridge? Okay, see, train, suppose it comes from that side. A is the front end of the train and B is the back end of the train. Total length of the train is given as 100 meter. Length of the bridge is given as 1 kilometer or it is 1000 meters. Okay, so when the front end of the train is at the beginning of the bridge, let us say train has started to cross the bridge. Okay, when do we say that crossing is over? See, when the train occupies, say, this position. See, when the train is here, we cannot say that that crossing is over. Okay, see, we can say the train has crossed the bridge only when the back end of the train is at the end of the bridge. Okay, so this is the final position of the train and this is the initial position of the train. Displacement is from the initial to the final. So any equation of motion, v equal to u plus at or s equal to ut plus half at square, any equation of motion can be applied for any points. Okay, suppose we are applying that equation for the front end of the train. So front end of the train A, from this point to this point. Okay, what is the displacement? From here to here it is 1 kilometer, and from here to here, that is the length of the train, it is 100 meter or 0.1 kilometer. So if you apply this equation for the front end of the train, then the displacement is 1.1 kilometer. If you apply for the back end of the train, see, this is the initial position and this is the final position. Okay, so from here to here the total displacement will be, this is 100 meter or 0.1 kilometer and this is 1 kilometer. So again it is 1.1 kilometer displacement. So we can write it as C S equal to 1.1 kilometer, 1.1 kilometer. Okay, then we have to find the initial velocity, we have final velocity, we have acceleration, it is given as constants. Okay, we have to find the time. So you might be thinking of applying this equation v square equal to u square plus 2as to find the acceleration first. Okay, if you get the acceleration from this equation, that can be put in this equation to find the time. Okay, because all other data, u initial velocity, v final velocity are all given, so you can find time. But see, when you put these values in this equation, either you have to apply this 63 as itself, or you can convert it into meter per second by multiplying with 5 by 18. Anyway, you will have to find the square of that. Okay, either the square of 63 and 36, or you will have to find the 63 times 63 into 5 by 18 whole square, or and also 36 into 5 by 18 whole square. You have to get the acceleration and put the value of acceleration in the second equation to get the time taken by the train to cross the bridge. But that is not the simplest method, that is not the right procedure to get the time. See, whenever a body is moving with a constant acceleration, the most beautiful, the most useful formula is displacement is always the product of average velocity and time. And average velocity is the arithmetic mean of initial and final. For any body moving with a constant acceleration, it can be positive or negative. What? Acceleration. Only thing is that it should be constant. See, in such cases, displacement s is equal to, as the acceleration is constant, average velocity is nothing but the arithmetic mean and time. The most simple and powerful, beautiful formula. Okay, so this is 1.1 and this is 63 plus 36, that is equal to 99, all in kilometer and kilometer per hour. So we will get the time in hours, okay, divided by 2 into time. Okay, so that time will be in hours. So what do we get? See, this is equal to 1.1 and 99. When you divide this, here it will be 90 divided by 2, that is equal to 45. So time t will be equal to 1 by 45 hour. Okay, see, this 1 by 45, this is equal to into 60 minutes. Okay, again into 60 seconds. This much is the time taken by the train to cross the bridge. This is this 45 and 60 you can divide both by 15. So here it will be 4 and here it will be 3. Okay, 60 by 3 will be 60 by 3, that will be 20 into 4, so it will be 80 seconds. So the time taken by the train to cross the bridge is 80 seconds. Okay, thank you.